Good morning. I'd like to thank the Eurosteel committee for the opportunity to present. This paper was written in 2019, and at that time I was at the very beginning of the experimental phase of my master's degree, which was part of a bigger and ongoing research program involving University of São Paulo, Institute of Technological Research, and CBMM, a Brazilian mining company. The focus of this research is the development of a new steel alloy with the fire-resistant properties using niobium and molybdenum working together in synergy. So what I'm going to present today is the partial results got from the first test in a pair of steel beams with different compositions, being one a conventional carbon manganese steel and the other one a fire-resistant steel. So this is two different views of the IPT horizontal gas furnace modified to run the tests of simple supported steel beams, which was loaded by means of two concentrated loads applied by a jack through a reaction loading against a moment frame steel structure. Thermocouples were installed in three different sections of the samples, and also inside of the furnace atmosphere nearby to the samples. In order to not allow the heat escaping and let the beams free to bend during the loading, three precast concrete slabs were installed above the top flanges. As I explained, two different steels with different chemical compositions were used, allowing us to compare the behavior of both steels under the same thermomechanical loading situation. The fire-resistant steel beams were produced in Japan according to the JIS SM490A-FR Japanese standard, here named as JP1, and the conventional steel was produced in Brazil according to the ASTM A572 grade 50 North American standards, here named as BR1. What is important to tell here is that the most important difference in terms of chemical composition between those two steels was the massive presence of molybdenum in the fire-resistant steel. Well, before running the tests itself, we did two sacrifice tests to see how the furnace would behave so as the beams, and it was observed that some limit states were reached in the connection part of the structure. By the way, it is important to say that the behavior of the connection was not the focus of this research. So for the official tests, we provided reinforces on the web, as you can see here, and a small chamfer at the bottom flange to allow freely rotation during the bending. And we did it to all 8 samples. This is a drawing of the system built for the tests and the position of the thermocouples over the samples. The criteria of both European and Brazilian standards for tests were met. From this slide on, I will present the results of the first pair of samples. These graphics shows how close the furnace temperature were to the ISO 834 standard curve. The left graphic represents the heating curve got from the stick furnace thermocouples during the JP1 test, and the right graphic represents the same for the BR1 tests. This graphics plots the heating curve of the JP1 sample in 3 different sections, section A and section C in the extreme of the samples, and section B in the middle of the samples. In total, 8 thermocouples were installed in the 2 extreme sections, and 6 thermocouples were installed in the middle section. This is the same graphics plotted here for the BR1 sample. This is a time and temperature versus displacement graphics for both JP1 fire-resistant steel, here represented in red, and BR1 conventional steel, here represented in blue. What we can see here is that the plastic deformation, or the limit test condition, has occurred 10 minutes later, or 100 Celsius degree heater for the fire-resistant steel compared with the conventional steel. And what we saw is that the same curve shape were seen for the other pairs of samples. Here we can see the absolute displacement values for both steels at the range temperature 400 degrees to 800 degrees, with the biggest difference occurring around the 700 degrees. Again, the red curve stands for JP1 sample, and the blue curve stands for the BR1 samples, being the JP1, the Japanese fire-resistant steel samples, and the BR1, the Brazilian conventional steel sample. This is a quick time-lapsing recording did in one of our tests. Here you can see the plastic deformation of the beam here and the behavior of the connections. As I said, another 6 tests or 3 pairs more of beams with different steels were carried out, but with slightly changes at the mechanical loadings. What we saw is that for the other tests, the same curve shape, but with the different magnitudes. Here you can see the 1, 2, 3, 4 pairs of samples being a fire-resistant steel and a conventional steel for each pair. Some points were discussed before the conclusions based on the results showing the beginning of the plastic deformation in millimeter and in Celsius degrees. As we can see, the other tests show different numbers, but always demonstrating the same ability to reach the plastic deformation when using fire-resistant steel. For the discussions, plastic deformations have occurred in different times and temperatures between different steel grades. Differences in absolute displacement values could be seen at the range 400 degrees to 800 degrees between different steel grades. Significant differences from the behavior of such different steels were not noticed at temperatures above 800 degrees. And the displacement versus time and displacement versus temperature curves shape remained the same under different loading intensities. This is the conclusions presented to the final Masters Board members. Highlighted in gray are the conclusions that came from the analytical part of my thesis. Actually, the complete work involved an analytical and numerical phase besides the experimental. And so, having this in mind, let's move on to the conclusions. Fire-resistant steels had better performance compared with the conventional steels when exposed to the same thermomechanical loading conditions. This enhanced performance seems to be more effective at the temperature range 400 degrees and 800 degrees. Below and above this range, both steels behaves the same way. The stability of the sample beams after certain temperatures and deformation, highlighted by the non-occurrence of the lateral torsional buckling, occur between other factors by the as-called catenary effect. As I said, this gray conclusions here is related to the analytical phase of my work. It is possible to obtain different critical temperatures or temperatures that must not be exceeded by the structural element under fire situation for both fire-resistant and conventional steels. That will result in the reduction of the protection material thickness to the fire-resistant steels compared to the conventional. Depending on the level of the exposition of the structural element during the fire, fire-resistant steels can eventually dispense the protection material when compared with the conventional steels. There is a good correlation between the tests carried out in laboratory and the analytical models proposed by the Brazilian national standards. So this is all. Here I have some acknowledgements, first for CBMM, which is a global supplier of niobium and the mainly sponsor of this research. To the USP, University of São Paulo, I want to thank you as well, and IPT, Institute of Technological Research. So thank you so much for your attention.